All right, we have an interesting problem here. It's saying we have a pendulum here. A stick of length L equals 1.6 m oscillates as a pendulum. So what's the value of, if we were to move the center of mass here, usually that's where the center of mass of a pendulum would be. But if we were to move it to, say, maybe here or some other point and call that distance x, if we were to look at our period, that would be t. We have an equation for our periods. Well, usually we have these three right here. There would be the simple pendulum, 2 pi square root of length over L. But let's go ahead and use the complicated one, the pendulum one, which would be 2 pi and then inertia over mg and center of mass here. So go ahead and use that one. I'll put that right here. T equals 2 pi square root of I over mgx center of mass. That's going to be the equation that would be able to solve this problem. Now we got to figure out what I is for this rod. Usually if we try to figure out the I for a rod, it would be, let's go ahead and use the parallel axis theorem to solve this. Parallel axis theorem. But the problem is, usually we would be thinking about, oh hey, you know, this is 1/3 because, here, let me finish this equation. I plus md squared. This is distance from the axis. Hopefully you guys know how to use this theorem. Anyway, so I equals, this is the center of mass. Usually we're thinking 1/3 because it's a rod like this, and we're thinking, let's use 1/3. If you're ever messing around with rods, specifically for the parallel axis theorem, go ahead and use 1/12 for the ml squared, for the coefficient in front, instead of 1/3. Don't use the 1/3 if you're ever messing around with or ever changing the inertia of a rod. For other things, this doesn't really happen. But I mean, anyway, it's just something to watch out for. It was a mistake I made. You're gonna want to use 1/12 here, not 1/3. Let's go to the next one. Plus and this is the distance from the axis of rotation here to the center of mass, which is, in this case, our new one is going to be x. Usually over, okay, well, let's just keep going. So we have this x squared and I. So let's go ahead and plug this into the equation. Put this over here at the bottom. T equals 2 pi square root of 1/12 ml squared plus mx center of mass squared. This is going to be divided by mg, and then here's the x. We don't need that. Just know it's an x. That's going to be our x. We're trying to solve for that. Okay, here's the next part of the problem. We need to ask ourselves, how are we going to figure out the least period? And this is where the derivative trick is going to sort of happen. There's two key points in this video. One is here is the parallel axis theorem using the coefficient of 1/12, not 1/3. And then the derivative trick is the second key point. If you're ever finding maximums or minimums of equations, well, this doesn't really work if it's a straight line, right? You're going to want to set the derivative equal to 0, right? Set the derivative equal to 0, and then you can find the maximum and minimums. It doesn't really work if you have a straight line like this, because then you'll find no maximum or minimum. But for every other kind of equation, there's going to be points like this where you'll find derivatives of equal to 0, maximum, minimum. Even for a line like maybe something like this, you'll find that you'll get some sort of a tangent line at some point. So that's what we're trying to do here. We're trying to set the derivatives equal to 0. And you could even possibly do this for maybe even setting it to infinity or something like that if you were going to do for something like this. But I don't know. Anyway, the point is, let's just keep going. So now we're going to ask ourselves, should we take the derivative of the entire equation? Well, it's pretty neat because we don't really need to. All we need to do is take the derivative of the inside, and that will give us the answer here. So that's what we're going to need to do here. Let's go ahead with 1/12 ml squared plus m. We're going to separate this out into two different denominators here. Separate them out like that. From here, we can easily see that, oh, I don't know, the m's cancel here, and even the 12 can sort of go on the bottom there. So we'll have this L squared over 12gx plus, and here one of the x's will cancel on top, the m's will cancel again, and we have x over g on that side. If we were to take the derivative of this, we can just do each side sort of separately. So that'll just gonna, let's split this up a little bit because it looks a little weird. You would think it's kind of complicated, but it's not. It's really more like this. Plus, and this is not the derivative yet. This is, I'm just rewriting this. Okay. So, and this is technically 1 over g times x. Okay. Here, I'll put the parentheses around the other side. So 1 over g, and then there's the x. So you can kind of see how easy it is now. This is just constants over here. So there's nothing to do on this side. If we were to take the derivative of 1 over x, we'd actually get negative 1 over x squared. And then we can put this back over here, 12g. And we go over here, 1 over g, and this will just turn into a 1. So if we were to rewrite this, keep in mind that we're wanting to set this equal to 0, and that this is actually negative. So I'm going to sort of skip ahead here, and I'm going to set them both equal to each other, right? Because I could sort of flip this to the other side, okay? And I'm going a little fast here, but the idea is we're going to go L squared over 12g x squared equals 1 over g. All right, just took this and moved it to the other side. Now, and take the cross products, I guess. It's pretty easy. L squared g equals 12gx squared. See the g's cancel, and we're going to get L squared over 12 equals x squared. Take the square root of both sides, and it turns out that x is going to be equal to L over square root of 12. Turns out that's our answer right there. If we go ahead and plug that into the calculator, we'll find, for our particular problem, we had 1.6 divided by the square root of 12. And then you're going to want to use that back into the period equation up here. So you can go ahead and use t equals 2 pi, and the square root of, you could figure out what the I is up here, but it'll just be essentially plugging back these values. We don't even need to rewrite this equation. We can just cancel this out, put in 1.6 here, put in the, sorry, not 1.6, this is 1.6 divided by square root of 12, 1.6 divided by square root of 12. If you go ahead and do that, and plug that in for your answer, you should get the right value. So I think this should have solved the problem for you. Don't really care too much about figuring what the actual answers are. It doesn't really matter. But I'll give you kind of what these were. This should have been 0.46. This helps you kind of think about whether this was accurate. Yours should have been a similar decimal. And then also over here in part B, this is part A. In part B, the least period is t equals 1.93 seconds. This was meters. And again, yours should have been a somewhat similar answer. If you plug those numbers in, I think this should have solved the problem. Make sure to like and subscribe. Peace.